Hello. In this section, we're going to look at another way to graph quadratics. To appreciate the new way, I'd like us to start by just reviewing what we've been working on recently. Recently, we've been working on graphing quadratics by factoring first to find the x-intercepts, also known as the zeros. So to start, I would like you to try graphing the following by doing just the first two steps. So I'd like you to just take maybe 30 seconds for yourself. Try these first two steps. Can you factor the equation to find the x-intercepts? So pause the video now for yourself. Maybe try doing the first two steps and see how far you get. So pause the video now. Come back after you've given step 1 and 2 a try. Okay, so let's go over it. So the goal was to factor the equation. The reason you would do that is because factoring the equation allows you to find the x-intercepts, which is the x values when y is 0. So in order to solve this equation, I want to know what x values and make y be 0. And to do that, I need to factor it, and I need to find two numbers that multiply to make positive 15 add up to be positive 5. Since both of these are positives, that lets me know that my two factors need to also be positive. So my options are going to be 1 and 15 and 3 and 5. But 1 and 15 add up to be 16, and 3 and 5 add up to be 8. Those don't add up to be 5. So it turns out that this is not factorable. We call it prime. Just like there are some numbers that are prime, there are some quadratics that are not factorable and therefore are also called prime. But the question is, so if this is not factorable, how are we going to find the x-intercepts? Well, the x-intercepts turns out that they don't exist. So how are we going to graph that if we can't even find the x-intercepts? So that's kind of the question for the day that's going to lead us into the topic, is how do I graph quadratics if I can't factor it and there are no x-intercepts? The graph for this actually looks like the following. There are no roots. So how are we going to do it? Well, what we're going to do is we're going to go back and we're going to look at equations that were factorable. So we're going to go back to situations that did have x-intercepts, and I'm going to point out a pattern to you that was there all along but would have been kind of hard to find or appreciate until we found ones that did not have any x-intercepts. So let's go back to ones that actually were factorable. So if I wanted to find the vertex for this graph, I would first find the x-intercepts. And how do I find the x-intercepts? I want to find the x values that make y be 0. So I set y equal to 0. And then I'm going to factor this statement. This quadratic is a binomial. It only has two terms. So I'm going to do greatest common factor factoring. I look and say, okay, what's the biggest number I can divide out of the numbers of 2, negative 2, and 5? And I can't. What's the most amount of x's I can divide out? Well, I can divide out 1x. So it'll be x, and then what's left behind is a negative 2x plus a 5. Now it's factored. Now I can ask myself, what two things can I multiply and make one of them be 0? So I know either this thing that I've underlined in green is 0, or this thing that I've underlined in purple is going to be 0. I could solve this one easily because I know, well, this would be the case if x is equal to 0. This one's going to take a little bit of work. I know I want negative 2x plus 5 to equal 0, so I would subtract 5 and then get negative 5 and then divide by a negative 2. And a negative divided by a negative is a positive, and so I get the two x-intercepts are going to be at 0 and at 5 halves, or 2.5. So if I were going to sketch a graph for this so far, I know here's the very first x-intercept at 0. And I go out, maybe here's 1, here's 2, here's 3. The second one's at 5 halves, which is 2.5. I know that this graph has a negative out front, so that means it's going to open downwards. So the graph itself, let's sketch it in red. The graph itself is going to look something like this. And I want to know where the vertex is going to be located. Well, we know the vertex is always halfway in between. And how do I get halfway in between? Well, I average these two. So I take these two values of 0 and 5 halves and divide it by 2. Well, that's going to make 5 halves divided by 2. And that will make 5 fourths, or 1.25. That would be the vertex's x coordinate. And then we know what the rest of the process would be. You'd put the x coordinate in for x to find the y coordinate, and you go along your way. But the goal right now is to recall how we did this, because this is the key that's going to be helpful here in a moment. So let's check using Desmos, make sure we did it right to show you. Recall we did it by doing greatest common factor factoring because there were only two terms. So in the graph that we've just found, looks like that, right? So there's my 0, there's my 2.5, and then the vertex's x-coordinate, there it is at 1.25. You'd have to do a little bit more work to find the y-coordinate, but there we are. So we did it right. So how did we do it? We did it by factoring when we could, and the x-coordinate for the vertex is always halfway in between, okay? I'd like you to try this one more time because what we're going to do here in a second is we're going to do it with just variables to get a formula. I'm going to ask you to do it once on your own with numbers so that you are confident that you're going to be able to follow along when we do it with the variables. So pause the video now, take maybe a minute, minute and a half for yourself to try finding the two x-intercepts and just the vertex's x-coordinate. That's all I want you to find is where are the two x-intercepts and then where's the vertex's x-coordinate. So pause the video now for yourself, give yourself a minute, minute and a half to try it. Unpause it once you've had a chance to try answering those questions. Okay, what you should have got is you should have got that the vertex was having an x-coordinate of 1.25. I'm going to go really quickly through that. The only thing you could divide out would be an x because 5 and negative 12 don't have anything in common. So you'd get 5x minus 12. We want to know when is y equal to 0. So we'd set this equal to 0. Then we say, okay, maybe this is one of the x-intercepts. If the first part was 0, it should be 0. This one takes a little bit of work. I want 5x minus 12 to actually equal 0. So I would add the 12 over, divide by 5, and I get 12 fifths. 12 fifths is also 2 and 2 fifths, which is 2.4. So my two x-intercepts are 0 and 2.4. Halfway in between that is 1.2. So that's what you should have got, because I just wanted you to find the x-intercepts and the vertex's x-coordinate. Because now what we're going to do is we're going to do this process with just variables, and that's going to get us to a really nice formula that we can use always. It actually turns out I can use it even if the original equation didn't have any x-intercepts, which is going to be super helpful because that's the case that we were looking to solve in the beginning. So find the vertex's x-coordinate by first finding the x value halfway between the x-intercepts. So I need to factor it at first. So I want to know when is y going to be 0, because that's where the x-intercepts are going to be located. And how am I going to solve this? I'm going to do it by factoring. A and B are variables right now that are representing numbers. I don't know what A and B are, so I can't assume they have anything in common, so I can't divide anything out between A and B. But if I look at the x's, this has two x's, this has one, I can divide one x out. So I divide one x out. What's left behind? There's an A, there's a single x left behind, and then if I divide an x out of this second term, there's a b left behind. So I'm left with the following two factors, two statements. I have green thing multiplying purple thing equaling 0. It means one of them has to be 0. This first case is easy. That would be if x equaled 0. This second one I need to solve. I know ax plus b could equal 0. So I subtract b, and then I get negative b, and then I divide by a. And that leads me to having the two x-intercepts being at 0 and negative b divided by a. So if I were sketching maybe a picture for this, let's do that. It might look something like this. I have 0, I wanted green. This other one's at negative b over a. I'll assume right now that a and b are positive, but it doesn't technically matter. They could be negative, but it'd be over here. I sketch in my graph, and now I need to find where the vertex might be. It could be opening upward or downward again, depending on the values of a or b. Well, it's got to be halfway between. I want to know where this is located, especially the x-coordinate, because once I get the x-coordinate, to get the y, I just put it back in the equation. In order to get this, I need to find halfway between these 2 points. And how do I find halfway in between? I'm simply going to average them. So the vertex's x-coordinate is going to be the average of these two. So 0 plus negative b divided by a, and then how do you average? You divide it by 2. Well, the top, if I add 0, that's simply going to be, I'm just going to use black now, negative b divided by a. Now that whole thing's divided by 2. Another way to write divide by 2 is multiply by 1/2. Remind that to yourself. Dividing by 2 is the same as multiplying by 1/2, and then how do I multiply with fractions? Well, I just multiply straight across. top times top, bottom times bottom, that's going to leave me at negative b over a times 2 is 2a. And that's the key finding, is the vertex's x-coordinate will actually always be located at negative b divided by 2a, and we just derived that. You're going to spend a lot of time in higher math classes deriving formulas. We just derived one of our first formulas. We just proved that the vertex's x-coordinate will always be at negative b over 2a. We did it for ones that had x-intercepts, and then we're going to use Desmos to show that it actually is true even if it doesn't have any x-intercepts. So the key finding is that the x-coordinate of the vertex will always be located at negative b divided by 2a. Note what a and b are. A is the coefficient for the x squared term. B is the coefficient for the x term. If there was a constant term at the end, that would be the c term. In relation to this, does a vertical shift change the vertex? What I mean by that is, does this work even if my vertex, or if my graph doesn't have any x-intercepts? And it turns out it does. I'll show you why. So here we just found a second ago, so right, if here's a graph, right, it's got x-intercepts, but even if I move that graph up, you'll notice the vertex is never gonna change in relation to its x location, its x coordinate. So even if it, like this blue graph, is not factorable because it doesn't have any x-intercepts, however, it still has the exact same x coordinate. Look, negative 1.25, negative 1.25, even though the blue one's not factorable because it doesn't have any x-intercepts. So this property will work even for graphs that don't have x-intercepts. It actually turns out it works even for ones that do have x-intercepts. So that allows me to actually graph any quadratics that are or are not factorable. And so we have a ton of properties now that enable us to graph quadratics. We know if the leading term a is greater than 0, the graph's going to open upward. If the leading term a is less than 0, negative, the graph's going to open downward. We know the axis of symmetry, which is where the vertex's x-coordinate is going to be located. That middle imaginary fold line is going to be at negative b over 2a, and that's because the vertex's x-coordinate is going to be at negative b over 2a. Once I have the x value of the axis of symmetry, or the x-coordinate for the vertex, I find the y value by plugging the x-coordinate into the equation like we've done all along, and then as always, the y-intercept is always at 0c. If I put 0 in for x, those terms disappear, and the y-intercept will be at whatever the value for c is. So let's put all this together and graph one that turns out I could not do by factoring. So goal of this one is to graph it by using the fact that the vertex's x-coordinate will always be located at negative b divided by 2a. So just to appreciate this new tool, if I try to do it the old way of factoring, if I try to find two numbers that multiply to be 5 and add up to be 2, there are none, because it turns out this does not have any x-intercepts. So I only have one tool now, and that's by using negative b over 2a for this one. So I know the axis of symmetry, which is where the vertex's x-coordinate is going to be. The axis of symmetry is going to be at negative b divided by 2a. Let's write what a, b, and c are here. A is 1, b is 2, c is 5. So let's write that. A is equal to 1, b is equal to 2, c is equal to 5. The axis of symmetry then, where the middle of my quadratic, the parabola will be located, is going to be at negative 2 divided by 2 times 1. That will make negative 1. So I have the axis of symmetry is going to be right there. That means that the vertex's x-coordinate is also going to be at negative 1. Now, how do I get the y-coordinate? I put negative 1 into the equation for x. So the vertex's y-coordinate will be at, put negative 1 in for x, I get negative 1 squared, plus 2 times negative 1, plus 5. That will give me 1 minus 2 plus 5. That should lead me to be 4. So I know the vertex is going to be at negative 1, 4, right there. The y-intercept is always the y value when I put 0 in for x, which will be this right here. So 5. I now have the right side of the graph, and then I could just reflect this blue point over to its mirror image on that side, and I have the other side of the graph, and voila, I've sketched the graph. Recall that this imaginary line isn't really part of the graph, the axis of symmetry, it's just there to kind of guide us, right? So this dashed line is just there as a guide. The real graph is the red portion. So there you are. Is this vertex a max or a minimum? Well, this one, we're going to talk about the difference here in a second. You probably could have guessed this vertex right here is going to be a minimum because it's the lowest point on the graph. There actually is no maximum for this graph because it goes upward and upward. So this is going to be a minimum. Going to have you try one on your own. So pause video now. I'd like you to sketch a graph of the following by using the fact that the vertex's x-coordinate is located at negative b over 2a. Find the axis of symmetry, the x-coordinate of the vertex, use that to find the y-coordinate, then state the y-intercept. So pause the video now for maybe 2 minutes might take you, and give it a try. And then unpause it once you want to see how it's done. Okay, here we go. We're going to do it kind of quickly. A is equal to 2 in this case, B is equal to 4, and C is equal to 3. So that means the axis of symmetry is going to be located at negative b over 2a, which in this case is going to be negative 4 over 2 times 2, which again is negative 1. That's not always the case. It's just coincidental that it's been negative 1 both times. The x-coordinate for the vertex is going to be at negative 1. The y-coordinate of the vertex I get by putting negative 1 into my equation for x. So 2 times negative 1 squared plus 4 times negative 1 plus 3. That'll lead us to 2 minus 4 plus 3, which I believe is 1. So right there is the vertex's y-coordinates at 1 when x is negative 1. And then the y-intercept is this guy right here is 0, 3. I have one side of the graph, and then I reflect to get the other side. So the graph is actually this black part here. And this graph, that vertex is again a minimum because it's the lowest point. If the graph opens upward, the vertex is going to be a minimum. So there we go. Just to kind of go over those last two terms, the difference between a minimum and a maximum. If you're graphing a quadratic and the y-coordinate of the vertex is a minimum, that will occur if the graph is opening upward. So a minimum is the lowest point for an upward opening graph. The maximum is the highest point for a downward opening parabola. There is no maximum if it's opening upward because it's going up and up and up. Likewise, there is no minimum if the graph is opening downward because it's going down, down, down. So last question they'll ask you in this section is to tell whether the following function has a minimum or a maximum value and then to state it. Well, we first know that this graph is going to open downward. So graph opens down since a is less than 0. A is negative 3. So that means vertex is a maximum because the graph is opening downward. Now we want to find it. So find the vertex. I know the vertex's x-coordinate is always at negative b over 2a, which in this case is going to be negative of a negative 12 all over 2 times a. A is negative 3, so that's going to give me negative of a negative up top is 12. Down below, 2 times negative 3 is negative 6. That leads me to be negative 2. If I know the vertex is x-coordinate, how do I get the y-coordinate? I put negative 2 in for x in the equation, so I get negative 3 times negative 2 squared minus 12 times negative 2 plus 10. It's going to be negative 3 times 4 plus 24 plus 10. Negative 3 times 4 is negative 12. Negative 12 plus 24 plus 10, I believe, would lead me to be 22. So the max then occurs at negative 2 comma 22. And if I show you the graph, you'll see negative 2, 22 is exactly what's shown here. So there you go. That is it for today. Thank you very much and have a good day.